All right, significant figures. I think significant figures get a little bit of a bad reputation, and that's probably rightfully so. However, they're super important. So, what we will do is talk about significant figures now. We will look at how to apply them in calculations, and you will apply them in calculations near the beginning of this class, and then you will use them in second semester lab if you take the second semester lab. So, significant figures, it's the same number of digits as if you were reading the value off of an instrument. And all measurements contain some amount of uncertainty. So, an example of what that looks like, if you're reading the volume of a liquid in this piece of glassware, which is called a graduated cylinder, the volume might not fall perfectly on one of the lines that's given. So we have markings that tell us a certain number of decimal places, and then we always estimate the last digit, right? If it's exactly on the line, the last digit estimate might be a 0. If it's in between the lines, then you will estimate based on how far it is from one of the other lines. And significant figures reflect that uncertainty in the measurement. Now, this can be kind of discussed in two different parts. So, one way to look at it is first just how many sig figs are there, or is a digit significant? And then the second thing that we'll do is when you have multiple measurements with different numbers of significant digits, how does that propagate when you do a calculation? So the first question of is it significant, or how many sig figs, we have, it's kind of broken down like a set of rules. I'm going to go through this with some examples. So first, all non-zero digits are significant. So in 28.03, the 2, the 8, and the 3, definitely significant. In 0.0540, the 5 and the 4, definitely significant. The second thing to consider are zeros that are interior. So a 0 that falls between two non-zero digits. So 408. Based on the first rule, we know that 4 and 8 are definitely significant. And then the 0 is kind of trapped in between them. That 0 is significant. And in the number 7.0301, we know 7, 3, and 1 are definitely significant. And then the two zeros in there, there's one trapped between the 7 and 3, and one trapped between the 0 and the 1. Those are definitely significant. Now, let's talk about zeros in different places. Leading zeros are not significant. Now, the two examples that I have here are both with numbers that are less than 1, because you're really only going to see a leading 0 if you have a really small number. We tend, you could technically write it in front of a bigger number, but we tend not to by convention. So in the number 0.0032, there are no zeros that are trapped in between the 3 and the 2. We only have leading zeros, and none of those are significant. In the number 0.00006, all of those zeros are leading. They only exist there to be a placeholder. So you can't communicate the value of this really tiny number without putting a 0 there, but it is not significant. It's just a placeholder that helps you tell the value of this number. Now, trailing zeros have two different cases. I'm going to say two cases plus one unclear case that we're going to do our best to rectify. So if you have a trailing 0 after a decimal place, it is significant. So 45.000. Those zeros don't need to be there to tell you the value of the number. We could have just written 45 and you would understand the magnitude of that number. Because we explicitly included the zeros after the decimal place, they are significant. So this number would have 5 significant figures. The number 3.560 is the same scenario. You don't need that zero to communicate the magnitude, but we did include it, so it is significant. Now, there's one more case. If you have something, a zero, before a decimal and after a non-zero digit. So it is there to show magnitude, but we have put a decimal place after it to give an indication that it is placeholding but also significant. So 140.00 is 5 significant figures. 250.6. Now, this also follows that trapped between two non-zero digits rule. This would have 4 significant figures. Now, this rule that we just did is before a decimal. But what about before an implied decimal? So what about 1,200 with no decimal place? Those zeros are there as placeholders. There's an implied decimal place after this because that last zero is in the ones place. It's unclear because we didn't explicitly write the decimal place. It's super unclear whether or not those zeros are supposed to be significant. So we will avoid this at all costs. The best way to avoid this is by reporting your answers in scientific notation. So for scientific notation, everything that I have written here is the same value, and it's also 1200. But when you write something in scientific notation, the number that you have before the times 10 to whatever power you need to use is all of those digits are significant. So if I write 1.2 times 10 to the third, the 1 and the 2 are significant. This number has 2 significant figures. If I write 1.20 times 10 to the third, the 1, 2, and 0 are all significant. So 3 significant figures. And if I wanted to write it with all 4 digits significant, I would write 1.200 times 10 to the third. We will also sometimes encounter exact numbers. So these are numbers that have no uncertainty, and because there's no uncertainty, they don't affect significant figures in calculations. This will usually come up when you are counting discrete objects. So if I say that I have 3 apples, right, and especially something like an apple, this macroscopic thing, you can tell whether or not that apple is whole. There's no uncertainty about whether I have slightly more or slightly less than 3 apples, if they all appear to be whole. 3 atoms. Now, it's a little bit harder to discretely count 3 atoms since they're so tiny, but 3 atoms, you can't go any smaller and still be an atom. So this is sometimes talked about as having an infinite number of sig figs. So, my example here, I've written 3.000000000. It has a lot of significant figures because it is that certain. We don't have the uncertainty in that measurement. The other thing that will be an exact number is a conversion and a definition. So the conversion between centimeters and meters, there's 100 centimeters in a meter. There are exactly 100 centimeters in 1 meter because that's the definition of the prefix centi. It means exactly 10 to the minus 2. You will also not count sig figs for numbers that are appearing in an equation. So, right, there's an equation to convert from the radius of a circle to the diameter of a circle where you multiply by 2. That 2 is an exact number. It's not going to count against your sig figs.